Hello, everyone. Thank you for having me. My name is Anelia Angelova at Google Research, and I'll be presenting Learning to See Beyond. We'll be looking at three topics today. First, future activity prediction and human 3D pose prediction. Secondly, we'll be looking at unsupervised video segmentation from instructional videos. We are looking at finding the atomic activities that make instructional videos to accomplish a certain task. And finally, we'll be looking at a mechanical search for a robot, which is trying to search and operate on objects on shelves which are hidden or occluded. First, let's talk about future prediction using adversarial grammars. What we're interested in is videos where certain activities happen, and we're trying to predict what activities will happen next. Note that some of the activities may happen simultaneously. For example, at the top, the person is dressing while standing up simultaneously, or later sitting on the chair, and so on. At the bottom, the person is holding book, opening book together, and then reading the book afterwards. We are addressing this problem using adversarial generative grammars. They allow us to be able to predict much farther in the future and to be able to also work with a higher dimensional data. And here is an example of some of our results. Here, a person is sat down and is currently sitting. So the next actions generated by our grammar are that the person may want to stand up. And if they do stand up, they will walk maybe. Or if they're still sitting, maybe they will want to drink water next or use a laptop or etc. We based our work on our previous differentiable grammar modeling of videos, which was presented at IIIA 2020. Here, for example, for a baseball game, we can look at the sequences and model each two subsequent sequences of action as a grammar rule. So, for example, after a pitch, maybe another pitch follows, or maybe a swing follows. And in this way, you may want to represent the rules themselves, and the rules themselves encode what potential next non-terminal within the grammar may follow, which of course is able to generate more potential actions, or a terminal, which indicates that you have reached the last action, and then you should stop the sequence. And then in schematics, you can look at it this way. Given the initial state, which is obtained from, let's say, a video backbone, which had processed several video frames, you can then generate an embedding for the rules. For example, r-dimensional embedding for a fixed number of rules. And this embedding now is able to generate one or more potential non-terminals or n-terminals, as for example shown here at the top. And we're using the Gumbel softmax to be able to generate more than one at each given time. And then with that, you can, after after expanding the rule, you can learn what next non-terminal corresponds to that rule and what terminal corresponds to that. And when you apply this recurrently, you're going to achieve a sequence. And so here, for example, if we represent this schematic like this, you can see that for each of our grammar rule, maybe you have we allow for two sequences to be generated, and then we can have a tree of with branching factor of 2 of many possible sequences to be generated. But of course, that's a drawback, because we have a very high branching factor and we are not able to model very, very long sequences that way. Now, so instead, in our work, we focused on adversarial grammars, And the adversarial grammar still use the grammar, the grammar structure to learn sequences of actions, but we also use a generator and discriminator, where the generator is actually our grammar, in order to be able to discriminate what the real sequence is and what the generated sequence is. By doing this process, we are effectively learning the underlying distribution, and therefore we're learning what is a meaningful sequences of actions within here. And more importantly, because we don't have this high branching factor now, we're able to work with high dimensional data, as is, for example, 3D human pose. For example, it can be 30 dimensional or more. And we are able to generate much farther in the future, being able to model longer sequences. Here are some examples. In, say, cricket scenario, after a swing, you have a catch or play or no play, or for preparing a salad, after cut tomato and cut cheese, then maybe the next sequence is a cut lettuce, add oil afterwards, or cut something else, and so on. Here are some results with video, with 3D pose predictions from video, and you can see that we're able to generate very meaningful sequences at 4 seconds ahead for this high dimensional data. And interestingly, for the same starting pose, we're able to generate various sequences that may correspond to walking, eating, sitting down, and so on. The quantitative results also show improved performance compared to previous work, and as well as the standard grammar. And similar result on another dataset, the multi-tumors dataset, where you can see at the far range, 30-45 seconds, our results are much better than previous work. These are the quantitative results for 3D pose prediction using standard protocols. We also outperform previous work in most scenarios. And interestingly, here you can observe that previous work is able to reach 1 second, where in our case we're able to reach up to 4 seconds, and as I showed you before, with very, very reasonable pose predictions. Now, I'd like to talk about unsupervised video segmentation, or how can we read instructions from videos without having supervision about neither what activities might be there or what their duration might be. So in this example, this is from the 50 salads data set. You have a video that shows how to prepare a certain salad. And it's a long video that many things are happening. What we wish to do is to be able to segment that in subatomic actions. And that is valuable because a robot may want to obtain these subatomic actions and use them for example, cooking or something like that. So while these videos are not supervised, and that is deliberate because supervision for videos is very, very tedious to obtain. These instructional videos, for example, frying an egg or changing a tire, they contain a lot of structure. There is certain sequence to things. For example, with changing a tire, things will definitely, with all videos that change tire, while there'll be a variety of viewpoints, persons, cars, etc., there will be certain structure to the sequence of first unmounting the previous tire before you put in the tire, and so on. We're again using as an underlying modeling our grammar modeling, but here the challenge is that we do not have supervision to apply to those terminals to be able to backpropagate what the actual action was, and everything is unsupervised. Instead, what we are doing is iteratively trying to learn, trying to propose certain sequence of actions, learning our grammar, and the grammar itself is able to embed what meaningful sequences are from the visual features, and then iteratively trying to improve what sequences we observe in the video. So here, for example, we are showing several generated sequences until we find the top performing one at convergence. And to explain a little bit more in detail, you can see at the first epoch, the sequences are quite random. And then as we go with progressively more and more training, we're able to obtain a segmentation of the video here to the right, where the activities are much more coherent and comprehensively represent the video. But while modeling that, we take advantage of the structure in the instructional videos, and then via losses, we impose several desired properties. For example, one of the desired properties is that we expect the duration of each of these atomic subactivities to be roughly the same. Secondly, we also may impose a loss saying that we don't expect an activity to happen twice. Of course, you can relax those for certain instructional videos. For example, for frying an egg, you may want to have some of them being repeated, but maybe you would limit how many times you can repeat them. And secondly, we expect them to correspond to the visual features, of course, and to take the whole video, as is shown at the bottom. And so here are some example results for changing a tire. At the top, you can see the ground truth. And remember, in our work, we do not see any of that during training. We don't know their names. So at the bottom, in the color boxes, we're showing the activities that we have inferred. And as you can see, they actually map roughly and correspond to the actual ones. Whereas for things like jack up, in our case, we think that there are two activities. Whereas for put on wheel and tighten wheel, visually, it looks to our algorithm as a single activity. And so here is another example, another video of the same type of instruction. You can see a very similar pattern here that a start to lose the tire is separated here in two. And one very interesting question arises as to how are we going to model the number of potential sub-actions. It is very similar to the clustering approach, where for each instructional video, there is a nominal value, but within range, a lot of values can work. And here you can see that for one video sequence, we are able to segment that into 5, 6, 7, and so on until 11 sequences, and they all correspond roughly to the activities happening in the video. And to me, this is amazing result because without knowing anything about these videos, you're able to segment them into meaningful atomic actions, which can be read by various of autonomous agents and used for various of activity, various of purposes. For example, telling you how to prepare a recipe, or even taking these actions and executing them on a robot. Our quantitative results are very strong here. In some of the data sets, we even see that our results are better than the weakly supervised cases, and we show results for 3 different data sets. Some interesting results for the 50 salads data set. I'm showing here the confusion matrix, and you can see an interesting phenomenon that actions, for example, cut cucumber or peel cucumber, are never confused, but cutting a cucumber, cutting tomato, cutting lettuce there are often confused. And of course, on the other hand, none of these cutting or slicing activities are ever confused with adding oil, spices, and so on. Here's some more results compared to state of the art for various videos, and our work is represented in blue, and you can see that it outperforms them across the board. And finally, I'd like to talk about a work that can help our lives. For example, we can ask a robot, get a soda from the fridge, or go find my medicine. And just highlighting that in today's robotics world, we have a lot of work on grasping, pushing, tossing, and so on, where objects are supposed to be, objects are typically random or crowded and so on. Whereas we're looking at a scenario where we would like to manipulate objects that are not immediately visible and then that are on a shelf. For example, we may want to get something from a fridge or something that is on a shelf, and we have to more carefully operate within those environments first. And second, we have to also try to find things that are not easy to be found, but we are not allowed to break things or shove them around too much. And I'm presenting our works, LAX-ray, lateral access search for unseen objects on shelves, which I'm very happy to be collaborating with the Auto Lab at UC Berkeley and the team there. And you can see at the bottom our project and our paper sites. So in this environment, we would like, as mentioned, to carefully manipulate the objects so as to uncover the object that we seek, and we have to be careful to not topple things and so on. Exactly the fridge or a shelf scenario. And we'll be performing mostly sliding actions. This work actually is based on a previous work of ours, again with UC Berkeley Auto Lab with Michael Danielczyk et al., where we were trying to find here by grasping an unseen object. You can see here as an example at the top where our object is fully hidden. We're trying to learn the potential occupancy distribution of where could this object be. We are not seeing it, but given that we have an idea of its size or maybe aspect ratio, and when we can see partially the table, we are sure that there are areas that this object cannot possibly be. And that actually informs our grasping strategies of which objects should we remove first, here shown by yellow, in order to maximally improve our chances of finding the objects. And when we do that by several sequences, we're able to find the object. At the bottom, we see that if the object is partially seen, the distribution shrinks to a point where we are very, very certain where the object is and which object we need to remove in order to uncover that. So we are applying a similar strategy to the lateral shelf scenario, where we are using a 1D occupancy distribution. At the top, you can see a partially visible object here shown in green, where we're very quickly finding our way to the object, whereas at the bottom, you can see that in the beginning, it's much more uncertain where the object can be, and we need to manipulate the rest of the objects in order to find it. So here is an example. Given the input image depth, we are building the predicted one-dimensional distribution, and you see it has several modes. We'll pick the highest likelihood of the object being there, and then select an action of sliding, for example, this object to the right, and we'll do that to the left, sorry, and we'll do that with the robot arm until the object is found. Here is an example of how this distribution changes with respect to the scene or the objects that are there, and also the object that we search. If our object is like a can, it is small, then it could be basically anywhere. Whereas if the object is tall, there are only a few places where this object can be. And here you can also see mostly uniform distribution in the first case and 3 modes in the second case. And so here is some example, a sequence of a manipulation sequence of the robot moving in order to uncover the object. And some example results in simulation first. And so here are some results with actual objects. You can see first the distribution is quite uniform here to the very left. And then we pick the best possible action, which is to move this object to the left. And then the distribution changes now, pointing to the right-hand side of the scene, where now we need to move some of these objects here until finally you can see that the objects is partially seen, by which the distribution peaks until it is fully seen, and the distribution is peaked again. Comparing to very strong baselines, we see that this approach is able to be much more successful in uncovering the objects and takes much fewer steps. And in conclusion, in this work, we attempted to look at what can come next, or what is not immediately obvious or seen. And we have looked at predicting future activity by using grammar modeling. Also, we applied the same grammar modeling for video segmentation without any supervision. And lastly, we talked about mechanical search for operation on shells where the object is not seen or partially seen. Thank you very much to my collaborators at Google Robotics Research and also at UC Berkeley. Here are the papers, and thank you very much for your attention.